Hi. So you guys just have probably started getting into stoichiometry, and today I'm going to be talking about limiting reactants, which is actually one of the more simpler elements of chemistry, yet one of the most important elements of chemistry. So let's take an example reaction. Let's say element A plus element B go to form some compound called AB. Well, the thing is, with reactions is when you have multiple reactants involved, such as in this case where there are two, some of the time not all of the reactions are used up. Like if we have more of element B than element A, when the reaction goes to completion, we'll still have some element B left over. This depends on the coefficients of the equation. It's relatively straightforward here because the coefficients of both of these reactants is 1, so you need one element of A for every element of B. But if the reaction was something such as 2C plus 1D to form something like this, as you can see, because the coefficient of C is 2 and the coefficient of D is 1, you actually need 2 times more C than you need D. So, in this reaction, if you don't have at least twice the amount of C than D, C is going to be the limiting reactant. So you might be wondering how exactly we determine the coefficients of the reactants and the products in the equations. In the previous example, I just gave them to you. But most of the time, we can balance equations. If we know the chemical identity of the products and the chemical identity of the reactants, we can just use logic to balance the equation. But another way to determine the stoichiometric ratio of reactants is through an experiment. And that's what I'm going to do in my demonstration today. So in my demonstration, we're going to take oxygen gas, and we're going to react that with hydrogen gas. Let's just assume that we don't know what the product is. We're going to try to determine what the ideal ratio of oxygen gas to hydrogen gas is. So you might be wondering how we determine the coefficients of the reactants and the products in a reaction. In the previous examples, I just gave them to you. But most of the time, we'll balance the equation. That means that we'll know the chemical identity of the products and the chemical identity of the reactants, and we can do some kind of logic to determine what the coefficients of the reactants and the products are. However, what we can also do is run an experiment, and that's what I'll be doing in my demonstration today. In my demonstration, we're going to take oxygen gas, and we're going to react that with hydrogen gas. And we don't really know what the product is going to be, but by reacting different ratios of oxygen gas to hydrogen gas, we can determine what the coefficients of each reactant is. So stay tuned.
Started stoichiometry. So basically, the purpose of this experiment is to determine the optimum ratio of hydrogen gas to oxygen gas in a combustion reaction. And we're going to assume that we don't know that it's 3 to 2, 2 to 1. It's 2 to 1. It's not 3 to 2. It's 2 to 1. So what we have here is we have 4 test tubes. These two contain pieces of zinc. This kind of zinc is called mossy zinc because it has been prepared in such a way that it has a very large surface area. These two test tubes contain manganese dioxide, which is a catalyst for one of the reactions we're going to do. And basically, we're going to use these test tubes to produce the hydrogen oxygen gas that we're going to use to light on fire, basically, to see how ideal each mixture of gases is. So,
do you have any worries that computers and things are in your way?
Maybe this one.
You might spill something?
This is basically a pipette head that has been marked so that there are 6, so that we can know what ratio of gases we have in each mixture. So we have 2 solutions: hydrochloric acid. 3 molar hydrochloric acid and 3% hydrogen peroxide. The hydrochloric acid is going to react with the zinc because zinc is more active than hydrogen. What's going to happen is that the zinc will replace the hydrogen in the HCl, so there will be H plus ions freed, and those H plus ions will form hydrogen gas. So this is a the other test tube has manganese dioxide, and then we add hydrogen peroxide. It's also going to start fizzing as it produces oxygen gas. Because naturally, hydrogen peroxide will decompose to form water in the upstream. But
Just too full? Yeah. You can use that as a beaker, right? That's not what you need to rub it.
Usually it will naturally, hydrogen peroxide will naturally decompose to form hydrogen, oxygen gas, and water. It takes a very long time to develop yeah, so this hydrogen, a hydrogen generator is going to be so hydrogen is produced much faster than the oxygen is. But right now, in that test tube, we have approximately a 5-to-1 ratio of 5-to-1 ratio
of hydrogen to oxygen. So what we do is, if you like hold the top of this close enough, it should make a popping sound.
That was a little more exciting. Don't put your face so close.
That was pretty loud. That's supposed to be the a scale of 5 on the loudness ratio. That's a lot.
They're just being watched.
A lot higher than the 5 would probably be. So so that's the.
I think it's simpler because you left it sitting on the oxygen for a while, and so it was replacing some of the hydrogen with oxygen.
But yeah, there's not supposed to be recoil until this one.
Just hydrogen to compare.
Oh, if I could hydrogen. I really just hydrogen. This is the. This is scary.
Yeah, that was a very good.
Okay, so this is like now the ideal ratio.
Less.
Oh, that's cool though.
That's a 10.
Like,
Sounds like a 10 to me.
yeah.
We could like do this forever, but I don't think we do this forever, and I don't really want to do it every year. I guess I'm just demonstrate like all oxygen and all hydrogen. Just have some reference points like that.
I think that's why they suggest putting it on a little platform.
Well, for the palm test, they just wanted like your classmate to hold the mat and just put it there.
Wait, this is scary.
So this is just hydrogen, so it should not be. The only combustion that should occur is any oxygen that's in the air, so it shouldn't be.
Yeah, that was your one.
So technically, it was like this, like a new single combination timer, but that takes forever. So after I do just oxygen, which just oxygen actually shouldn't even pop because oxygen can't combust because it's oxygen. Combustion is a reaction of oxygen. But now that we've determined the most explosive combination, we're gonna like be NASA and launch a rocket. Maybe I'll show the hydrogen this one all the way to the oxygen.
Can you just use where it's been partially filled and just turn it upside down and have the oxygen come out to the top?
Right, yeah. That's what's gonna happen next. two sets of test tubes each of them in case it slows down too much. Basically, what this is going to do is it's like a. Where
Do you need some light? Oh, sorry. Go ahead.
I assume it's like it's. I don't know whether I know like you can make one of these from like a old lighter. Basically, it's just going to be a spark between these two pieces of copper, and if we have the right ratio of hydrogen to oxygen gas, a spark should be all you need to start the combustion reaction. So we're going to put this spark maker inside of.
Oh. I already don't like this. Oh, thank you.
That's last time we did it.
I think you might. Did you put it on too far?
Yeah.
Last time you just barely put it on the end.
Put it again.
It's up to you.
Okay. Well, were you gonna ask me something? Or were you gonna talk about it? I guess.
Oh no, I was going to ask you if you were going to leave some water in it
So you can propel it.
to propel it.
Right.
But I don't know whether it would work as easily the way just the design that you have.
Leave water in it to propel it. Like, what do you mean?
The gases would push the water back,
Yeah.
and that would then the water moving back. But if you just have the gases moving, expanding, pushing.
This is kind of like water on.
Are you all set to go now, Taylor?
Oh yeah,
Okay.
my computer doesn't.
You can set that up. And then,
Why don't you go up and set up all these filling these little tubes?
unless lock it up.
Nathan, it should be still filming, right? Although it's in the lock screen.
Well, you've been filming this the whole time.
Yeah, it's gonna be loud. I have to edit it once. But no matter how I edit it, my genuine video will still remain throughout. Good. Look at that. Okay, practiced it.
What you're going to do is you're going to do it where it's towards where Taylor is, but Taylor's going to move out of the way.
Alright.
So you're not shooting it towards us.
Ooh!
There we go.
And it felt pretty warm.
That's pretty good.
Okay, Dave's busy.